Right. So, then we follow it. There are, based on this kind of concepts, one can find out what is the condition for flashover to occur. So, time of burning I have already said, if you know the total area, total area, if you know total area of the room and this is the fire load, I should have used small q actually, because this is, so this q capital or small, whatever it is small, that is actually the fire load per unit area multiplied, let us say total floor area if I do, or whichever way. So, this essentially is the total quantity of fire load in the room divided by this will give the time of burning, that I have already told you. So, tau time of burning one can calculate out based on this formula. Now, empirically people have seen no flashover condition occurs if AW h to the power half is less than 0.8, right. If AW h to the power half, then no flashover would occur, because you won't have simply sufficient oxygen to cause burning of all the fuel in the room. What is flashover? Flashover is that point where everything starts burning. Now, if I do not supply oxygen, it will extinguish itself. So, that is the condition. Also, this corresponds to rate of burning used to 80 grams per second for wood. Actually, from this approximately one can calculate out rate of burning, and this is 80 grams per second. So, if the rate of burning is less than 80 grams per second, it will not have flashover, it will just extinguish itself. Beyond above limit, lower limit of burning for flashover condition is a function of ventilation factor. So, beyond above this limit of burning of for flashover condition is a function of ventilation factor, and this limit is given as that 50 plus 33.3 AWH to the power half grams per second. So, if it is less than 80 grams per second, rate of burning which you can calculate out 0.9 0.9 AWH to the power half, it was there, there is that formula that we talked about, 0.09 grams per second. Was it grams per second or kg per second? It was kg per second. So, kg per second, now multiplied by obviously point, so accordingly you can find out what it is. So, if you find out that m dot is more than this value, then this is flashover condition occurs. So, at this burning condition flashover will occur. So, you can find out that, actually one can find out this. So, these are again empirical. Now, using this people have tried to model the time temperature curve. If I know now rate of burning, as I said, I know m dot b, which is rate of burning of the fuel, which I know, I said 0.09, it was sorry 0.09 was 0.9 was, yeah, for this one only, oxygen was 5.526, 0.09 AW h to the power half. Now, then the amount of heat generated will be delta, like the Q would be Q for burning, rate of heat flow would be 0.09 AW h to the power half into delta Hc. Now, this heat has to dissipate to the outside. This is the rate of heat generation, this is the rate of heat generation, Q dot rate of heat generation, this is the mass burning, and delta H is the heat of combustion. So, that is the rate of heat generation. So, rate of heat generation, this must be, this is the heat generated here. This many books uses them as small QC, heat of combustion. This must go out through this by conduction through the wall, ceiling, roof, whatever it is, to next room, or if this has got good fire resistance, it will not go to the next room or next room. And then what will happen? Hot gases goes out through this, hot gases goes out through this. So, there is some kind of a heat flow taking place, because the temperature of the gas that is going out is high. So, if I know the rate of that amount of gas going out, that multiplied by the temperature difference into specific heat, mass into specific heat into temperature difference. So, hot gas goes out, it takes the heat along with it. How much is its heat content? It is its mass, mass flow rate, rate of heat that is going out, multiplied by the specific heat of those gases into the temperature, because it goes to the atmospheric temperature. So, that this much heat will take out because temperature is higher. So, like ventilation heat gain, ventilation heat gain, ventilation heat gain, amount of air coming in, it comes at some temperature, and if the room temperature is different, it will either take the heat, or if it is hot air, the room air will get heated up. So, that is equals to mass into specific heat into the temperature difference, or here mass flow rate. So, hot gases flow rate, if I know, some heat will go out by this. Some heat will go simply by radiation heat exchange. So, this is not exactly a convective phenomena, but related to the convection. Hot gases go out and radiative heat flow would also be there, because this phase surface is hot. This is hot actually. Air enters here, this is also warmer. So, this fresh air at room temperature enters. So, this is hot gases. So, at the hot gases there will be temperature difference. So, radiation heat gain is there. So, heat generated is actually transmitted to outside by conduction through the surfaces, radiation from the flame, and the hot gases going out. So, I can write an heat balance equation. Now, what is my unknown? The inside temperature, gas temperature, which changes with time. So, time temperature curve, if one wants to find out, one will have to solve that heat balance equation, because Tg, the gas temperature, is unknown, outside temperature is known, and one can solve for this. Now, this solving would be real complicated because it is a non-linear equation. I am not going to do that for you, but I just want to say people have developed such model, and CFD model uses this. So, if you want to use CFD model somewhere, some of you are using, people do use them, they do modeling without understanding the physics behind it. So, I am trying to give you the idea of physics behind it, right. So, that is what is done, the heat balance equation is written. So, total heat generated must be equals to heat loss by rate of heat loss due to replacement of hot gases by cold. Cold gas comes in from the bottom, hot gas goes out. This is the conduction, rate of heat loss through wall, ceiling, floor. This is the radiation heat loss, and this is some amount of heat loss would be there. QR is the rate of heat radiation, rate of heat storage in the gas. So, because what is heat storage? Temperature of the gas is increasing. Temperature of the gas is increasing. So, if I know the mass of the gas inside, its specific heat in temperature change in unit time, that I can find out. This is known to me because we know rate of burning. This I can find out, I can get an expression for this in terms of the inside gas temperature. This also I can find expression in terms of inside gas temperature. This also will involve inside gas temperature. We shall see these expressions. Some of you have not done possibly a any course related to heat transfer. I will quickly give you some idea, and this is also related to the inside gas temperature previous time to next time, right. So, one can express this in terms of finite element or finite differences, because there were differential equation involved. Let us see how it is. Now, somebody might neglect this or whatever it is. So, QC is this we have already seen, multiplied by delta HC. Radiation heat transfer is a little bit of problem here. It is T gas to the power 4 minus, it is governed by Stephens-Boltzmann law. So, radiation law, if would have done it in school or otherwise, or if you do not remember, let me tell you, the radiation is proportional to radiation heat exchange between bodies is proportional to T to the power 4 minus T0 is the outside, multiplied by Stephens-Boltzmann constant 5.7 into 10 to the power minus whatever it is, 6.7 into 10 to the power minus 8 watt per meter square per, this is not degree, Kelvin to the power 4, because this is an absolute temperature 273 plus, and this is called equivalent emissivity, because a perfect black body radiates everything, absorbs everything, equivalent emissivity, all right. So, equivalent emissivity of the window area, flame and air, that one can find out, and AW is the area of the window, because this is rate of radiation heat transfer is proportional to this temperature difference, and this is Stephen's Boltzmann constant. This is the equivalent emissivity. This is per unit area multiplied by area of the window, because radiation is taking place from area of the window. Now, this is this Tg and T to the power 4 minus T to the power 4 is this very much there, and this is anyway this is ambient temperature, this is the gas temperature. So, one can simply simplify this a little bit, but because one can simply simplify this a little bit by taking this value as nearly, if I am interested in rise over ambient, so I might take this datum point as T0 itself, and this one can in fact do some, one can write in terms of the amount of heat going in is proportional to, because this will be small compared to this will be 1000 plus 273, let us say. This will be how much? 273 plus 25. Take to the power 4, take to the power 4. Now, this value will be very large, very large. So, one can approximate it in this manner, So, radiation heat transfer, but the problem comes, you can see that this is nonlinear. So, you just can't, just like that you can't solve it. Is Tg to the power 4, and Tg is my unknown. So, you can't solve it, because just like that is more complicated than this. So, solved by trial and error method, and EF is given by 1 minus e to the power some constant x f. So, this is flame thickness, emission coefficient 1.1, roughly these are the values. Again, I am not interested that you calculate this, because that would take my 90% of my course if I actually or at least 20-30% of the fire part of same time as this. So, I am not interested, but I want you to understand what factors govern, that is important. So, flame thickness is this, and this is this is the mass flow rate of gas QL, mass flow rate of the hot gases going out, specific heat of the hot gases multiplied by the temperature difference, because cool air comes at room temperature, same amount of mass goes out hot gases. So, specific heat of the hot gas multiplied by the mass rate, flow rate, that is the heat it takes out, and then this is known to us actually, the air amount of air coming in. So, this I can put in here, and we can get an expression of this form in terms of AW h to the power half. Tg is my unknown so far, Ta is the ambient temperature. Here I can't neglect Ta, ambient temperature, because the temperature would be 1000 minus 25. So, something of that kind would be there. I can you can assume more or less not very large. So, conduction heat losses from the wall, that has to be done using Fourier's Bayer's heat transfer law, heat transfer equation. Tg is unknown and conductivity is a function of temperature. So, it is a nonlinear equation, nonlinear problem, and you can only solve this by trial and error. Now, what is this equation? Okay, the equation, I hope I have given the heat conduction equation. Let me see if I have given it. Right, no, I have not given it, because I assume that people would be knowing the heat conduction equation. Basically, what you have to solve is del square T del x square, right, and alpha or K, which is a function of temperature, equals to rho C, which is also function of temperature, into del T del T. So, this is the heat transfer equation. So, this parabolic nonlinear, because K is a function of temperature, rho C is a function of temperature, and we write K by rho C, we call it thermal diffusivity, written by, sometimes denoted by alpha, some people denote it by A, and in my case, in this case it is A is a function of temperature. So, this is every step you do not know the temperature to start with, so you do not know the conductivity. So, you can't solve it easily. It's a nonlinear equation. So it's solved by trial and error procedure, by assuming a value and iterating it and finding out. We are not interested in this. But I wanted to give you this equation and give you the understanding what it is. Boundary condition is unknown, Tg is unknown, so it makes its life even more complicated. If I want to solve this differential equation that I showed you, alpha as a function of t, del square t del x square is equals to del t del t. If I want to solve this equation, then if I need two boundary conditions. Outside condition at x equals to L, t is equals to Ta, I can say, outside boundary, and at x equals to 0, Tg, t equals to Tg, which is unknown. Initial condition, I can assume that everything at ambient. So you see, boundary condition is unknown. You go to for unknown boundary conditions, an inverse kind of a problem. It becomes problematic. So one can solve this by trial and error procedure. One can solve this by trial and error procedure, right? And people have actually done this. Peterson has obtained some of them. I am not interested in again solving it for you, but some people have solved using, let us say, a finite difference scheme. So you divide this wall into separate, several layers, write the equations for every layer, time steps, at every time step do iterations. It will have a hell of a lot of computational. Today, of course, it is very easy. So many CFD model does it, or do solve it by finite element or finite difference. Numerically, you can solve them. Okay, by solving this, people have derived this kind of curve, post flashover time temperature curve, time versus temperature curve for various fire load and ventilation condition, various fire load and ventilation condition. It is given in tabular form also. You want to approximately find out for a room, you can find out. But you want to really do it, do model, find out, simulate in a model, then you have to use modern CFD models, which will give you, right. So typically this is a function of the fire load and whatever, fire load as well as the ventilation condition. These are the kind of curves that you would have. Time, various opening factor values, various opening factor values, various opening factor values, and these are the fire loads. So low fire load to high fire load, that is it. So theoretically it is possible to simulate them. They all, at least pattern wise, they match. Exact value they may not match with the real fire, but if somebody is trying to do fire design, structural fire design, this has to be coupled with the structural design part of it. And people, they Abacus or Simulus or some of the softwares, they do it actually. They combine this and complete fire design of the building can be done. And this is a new area of research. There are a lot of activity going on this line in the world over last about 9/11. After 9/11, a lot of thrust has been given to fire design. The failure was because of the explosion. The aircraft went in, it exploded, there was a fire, and this fire led to collapse of one of the floor, which fell on other that structural failure. So huge research, for example, Michigan State University, they do huge fire lab. There is a old hangar, I don't remember the university, I forgot about the name, the gentleman, there's an Indian, but Drysdale, who has written a book from where I have collected most of this this knowledge base of fire dynamics. They have huge hangar, Second World War, hangar left. It's not being used anymore. So they use it as a fire laboratory. So make a full structure, sort of full beam, full size beam, column, and test them. Huge costly research actually. But there are a lot of fire research thrust. England has been doing, UK they have been doing a lot of it. Most of the ideas actually developed in UK earlier, and Canada. The Canadian, the National Research Council of Canada or whatever it is, they have been doing. US, they are doing now a lot of this. And structural fire design is even Hong Kong I find people are doing structural fire research. So structural fire research is trying to design the structure so that if the extreme fire goes in, structure will remain intact. But safety of people doesn't depend only on the structure. Much before that we have planning and things like that, which we will look into. So our idea is fire protection, not structural fire design. But if somebody of you are interested in structural fire design, then you have to get into this fire dynamics as well, right. So, I just try to give an explanation, right. For our purpose, these tables etc. are available and get some rough ideas, that is fine. So, that is related to structural fire design, that is related to structural fire design or fire fire dynamics, not fire design. Fire design I'll just cover right now. Fire design part of it, simple ones, very simple, because design for a given fire resistance, that is what we will do. But before that, we got to understand the material behavior. We got to understand the material behavior. How does material behave? Because you want to find out, do structural design, one thing is finding out the temperature, heat transfer part of it, but then this heat affects the material. Material properties changes with temperature, and then properties, there are several effects. One is that I will be interested in the thermal property change. Why? Because in heat transfer calculation I need them. I will be also interested in their strength, how strength reduces with temperature, elastic modulus, right, and similar sort of properties. So, we will look into now properties of material, how fire affects the material properties. For example, most commonly used construction material is concrete. So, let us look at concrete. Now, concrete it is basically made of inert aggregate system bonded by cement hydrates, right. Cement hydrates bond them, it is a particulate system, and basically you have something like this. You have particles of finer size, different sizes, particles of finer sizes, right, and inside there will be hydrated paste, right, cement hydrates. Well, you can have something called epoxy concrete. Now, in epoxy concrete, this binder is epoxy actually, epoxy a glue hardener which solidifies. So, basic one understanding of concrete is, simple understanding is, you have inert particulate system and the void space in between them, they have to be put together, right. The void space between them is minimized and you fill in the void space in material, which can hold them together by largely mechanical bonding, because inert material do not react. So, aggregates do not react, they are inert material, by mechanical bonding, or at best in some cases maybe van der Waals kind of bond. In between, some chemical bond could be there once in a while, but the binder itself must be well bonded with itself. So, cement hydrate should bond well with itself, it should not break, and the bond between the aggregates and cement hydrate, that is also an important. So, that is basically concrete. Now, so therefore, this is most important. Aggregates are natural material, many of them would have come from the volcanic source. So, actually formed at very high temperature, and then over the years they are there in the nature. So, they are inert and may not get affected till you go to the temperature of their formation. If you go to temperature of their formation, they might start disintegrating. Okay, some aggregates can disintegrate earlier, we will see that. The vulnerable one is this, because this is man-made at ordinary temperature through the reaction of cement, right, this is the vulnerable portion, right. So, this is what we call calcium silicate hydrate, gelatinous structure. So, we call it CHS gel. What is calcium oxide? Some of you would have forgotten your SiO2 stands for S. Now, this can have some N, some value N, M, right, and H is nothing but water. So, X water. So, this is the kind of structures I have, chemical structure I will have, which is the main product of hydration, cement hydration, ordinary cement, or all the modern kinds of cement they are there, which are lime based cement. They are one of the products of hydration will be this, and this is vulnerable to heat. Aggregates are not. Aggregates are not so vulnerable. Some aggregates are vulnerable. Sand, quartz formed over the years, they are natural material, they are not so vulnerable. So this is vulnerable. See, this is vulnerable. So what happens? This has got this H2O. First, when you start heating them up, there will be free H2O. Because this system is CHS, this system is capillary porous. This system is capillary porous. Now, why it is capillary porous? Because the reaction process of cement and water, the product occupies less volume than cement and water combined. First you have cement, let me call it Cm, plus water H. Now, the volume occupied by these two and volume occupied by this product which is formed, right, product which is formed, this was product is more, it would have expanded. If the product is less, then some volume will be left. Now, normally what happens is, generally you have cement, something like particulate system, let us say, it will hydrate, it will hydrate, it will hydrate, and some of it will get consumed and hydration product will come here, and there is additional water we add to make it flowable, otherwise I can't compact it. So, this additional water which does not react, it will evaporate out, leaving what is called capillary pores. So, this system is, cement hydrate binder system is capillary porous. So, I will have some water in the beginning in the capillary pores themselves. As I heat, this water will simply evaporate out, I have no problem till that point of time. So, up to 100 degrees centigrade, I do not mind, some water will evaporate out, there will be some amount of shrinkage, some shrinkage would occur, because as water goes out, there are it would some loosely bound water in this system also tends to go out. Structure changes a little bit, like clay swells. You take water out of clay. I do not want to go into the concrete technology part of it, science part of it in this class. Now, given analogy, clay, if you add water, it swells. If you withdraw out the water, it shrinks and might crack also. So, such kind of thing will occur up to 100 degrees centigrade. Beyond 100 degrees centigrade, 110 degrees centigrade, 200 degrees centigrade, this water is actually chemically bound, water of crystallization. They start actually getting disintegrated. They go out from the CHS system, they go out from the CHS system, right, they are disintegrating themselves. So, they go out from the CHS system, all right, and once they go out from the CHS system, it starts actually losing its its own binding property. That means, this material, the layer which is actually binding the paste, the hydrated paste which is actually binding the aggregates. Now, paste itself, its own bond gets disturbed. So, it tends to become powdery rather than a bonded single solid. When this bond does not exist, it is almost like a pack of sand and aggregate and find some fine particle, loose particles. So, beyond 200 degrees centigrade, this water starts going out. Up to 400 degrees centigrade, most of this water will go out, resulting in loss of bond and strength. So, gradually there is a loss of strength and bond up to 400 degrees centigrade. But beyond that, one of the product of this hydration, cement hydration, is calcium hydroxide. You see, cement is produced from calcium carbonate. By burning calcium carbonate, you produce calcium oxide, right? Carbon dioxide goes out. Now, this calcium oxide cannot be stable because it is not a natural material. So, in presence of water, it becomes calcium hydroxide, and in the long run, it takes carbon dioxide from the atmosphere, and for million years, if you leave concrete for million years in atmosphere, it will go back to its stable state of calcium carbonate again. From where you have got from the nature, it will go, I mean, in an ideal condition. So, anyway, here the point I am trying to make is calcium hydroxide that is there in the cement system. This starts disintegrating. This starts disintegrating, and I'll have now calcium oxide and water again going out. This occurs around 600 to 700 degrees centigrade. And after that, if you 800 degrees centigrade you touch the concrete, you will find ashes, white ash only. So in a post-fire building, if you want concrete structure, if it has reached 800 degrees centigrade, you scratch it, everything will simply come out. So that's the behavior of concrete. Concrete under fire, that's how it behaves, right? So that's how it behaves. So that's the thing. So we'll look into, we'll just quickly look into this in the, after I respond to some of your questions. So a little bit of concrete we'll look into, right? So that's what I said. So just putting them in words, cement has got a specific surface, that is surface area per unit mass by 300. The hydrates have got very high specific surface, and more than 1000 times of the cement, some of this cement concrete science issues. Hence it has got very large surface. So surface force is dominant and they bond each other. Cement hydrate bond with each other, and that's properties of concrete is governed by that. So water bonded chemically, I mentioned CHS. It also has gel pores which contain gel water, which is actually adsorbed water, like clay water, adsorbed. Adsorbed water is electrostatically bound water, and there are capillary pores, as I mentioned, and you have capillary water. So CHS gel has chemically bonded water, adsorbed water, and then you have capillary water. So up to 150 degree capillary water evaporates. There is no change in the structure, only some surface energy has been added, which will make it try to absorb water. If dry it, and again it will absorb some. So it's almost not exactly reversible, but nearly reversible process up to this. 200 to 400 degrees centigrade, the absorbed water is lost, adsorbed water is lost. There will now be shrinkage, and since it's under restraint, there can be cracks also, large cracks at 200 to 400 degrees centigrade. The gel structure starts to collapse. That's what I just mentioned. The heat starts attacking the water, which is bonded chemically, and the cementing property is lost completely. So 400 to 600 degrees centigrade. Beyond that, calcium hydroxide will break down, and entire concrete has degenerated completely. So properties change accordingly. 100 to 150 degrees centigrade, not much of an effect, strength would not reduce. 200 to 400 degrees centigrade, shrinkage, cracks, etc. you will find large as you go towards the higher temperature. Strength starts reducing beyond 200. 400 to 600, chemically combined water is gone, strength is practically, almost all strength is gone. And 400 to 600 and above, calcium hydroxide also breaks down. In fact, it is almost like ash, it's simply ash. So that's the concrete behavior on heating. Residual strength reduces progressively up to 800 degrees centigrade. There are no structures, and you will find spalling of concrete will actually start occurring. Chunk of concrete will come down if you subject it to 800 degrees. So if you have gone to a post-fire a structure where there is fire has occurred, let us say even a bridge where the concrete or PSC or RCC bridge, and you find that chunks of concrete has come out in certain portion, you can rest assured that they are 800 degrees centigrade or near 800 degrees centigrade would have reached. You will find reinforcement exposed and almost as like concrete. Some aggregates like calcium limestone aggregate, they actually break down at 600 degrees centigrade, to calcium oxide to calcium carbon dioxide, 600 and above. Now what will happen if I have such an aggregate inside, suddenly it will burst out. So you have explosive spalling if you have limestone or magnesium carbonate aggregate. All carbonate aggregates, they break down like this kind of chemical changes, or magnesium carbonate will also break down into magnesium oxide and carbon dioxide. These are explosive in nature. So they just simply spall out cause the spalling of concrete, right? Spalling of concrete. So people have actually done experiment to find out the properties of aggregates, I mean concrete with temperature. So, this is what they have found here is proportional strength versus temperature. Now, there is complication in measurement. In fact, at IIT Delhi we have some facility been established by Dr. Basant Mahasagar, little bit he has done. I suppose Roorkee they have, and as I said, Karnataka there is NI, National Institute of Engineering, they have. So, some in CBRI of course they have, some places there is a facilities there. Now, if you want to test the material, how do they behave at high temperature, what you can do? You can raise the temperature, keep it constant, and then measure the strength, compressive strength for concrete. Okay, this is one of the ways. Other way is I load it, increase the temperature. Then also it will fail at low load. So, this could be stressed already. This could be stressed already. This could be already stressed, and this could be unstressed, and this could be subjected to temperature, say 400 degrees centigrade, and cool it and stress it, I mean test it. So, this is called residual, unstressed residual. This is unstressed, raise the temperature, then say 400 degrees centigrade, raise the temperature of the specimen. The compression testing machine is capable of containing a specimen at 400 degrees centigrade. So, it will first raise the temperature, hold it there, then the compression will be done, so such system. So, specimen will be heated up and then the compression load will be applied. This is unstressed. Stressed means I just stress it to 20%, because structure will be stressed. So, stress it and 20% stress of the failure. If I know the FCK value or strength value, cube strength expected, stress it to 20%, then raise the temperature to 400 degrees centigrade, then fail it, or 600 degrees centigrade, then fail it. But at ambient temperature is stressed to 200 degrees centigrade. So, there are different mixes they did, people have done such experiment. So, you find that with temperature strength reduces, uniaxial compressive strength reduces. Proportional strength is 1. If I take proportional strength as 1, which is unstressed at ambient temperature, that is I am calling as relative strength I am finding out. Divide every strength by the normal strength test that you do, then you get, this is proportional strength. You find that strength comes to, if it is 20% strength at 600 degrees centigrade, you will be left with only 40% strength. So, if your concrete was showing 35 MPa cube strength was there at ambient condition, at ambient condition, if you are subjected to 20% stress and then raise the temperature to 600 degrees centigrade and then again test it, you will find only 0.4 into 0.35, that means around 14 MPa or so, right. And if it is unstressed, then you find it still unstressed, still lower, you will find it around 600 degrees centigrade, something like 25% or 30%. And if you heat it up to 600, cool it and then test, you find still less, 20%. So, you will find about 7.5 MPa. So, post fire structure strength is much lower, but it is a function of temperature. People have actually fitted some equation, simple equations we will look into and then fix. So, this is the kind of behavior of stress strain behavior of concrete. This is the kind of stress strain behavior of concrete, all right, stress strain behavior of concrete. So, this is stress strain behavior of concrete, and you find that this is the at 375 degrees centigrade, this is the kind of scenario. At 700 it is like this, at 575 it is like this. So, what happens? It is normally concrete is brittle, 200 degrees centigrade. 375 you find slight increase in strength, I will discuss this sometime later on. As your strength increases, as your temperature increases, it tends to show a lot of deformation capability, but strength is much lower. That means it will have a lot of cracks developed. a lot of cracks developed. At 700 degrees centigrade, you are doing the stressing it, already cracks have developed, and it will go on developing more cracks and more cracks. So it can show a lot of deformation capability, where here the failure is quickly and brittle. So this is the stress strain behavior of concrete, and I think we'll repeat this. This is the elastic modulus of concrete, which also reduces its temperature, and then we'll look into steel in the next class. So I think we'll stop here.